monthly CASTA webinar. My name is Jeonghee Min. First name Jeongbom, last name In. I think In is kind of rare last name in Korea. So I'm serving as a vice president of the CASTA, and it's my great privilege and pleasure to introduce our two speakers today, Dr. Jeonghee Rho and then Sunjae Kim. So I'm gonna go and start introducing a first speaker, Dr. Rho, with a brief bio for you to get to know her more, and then we'll let her speak her presentation. So Dr. Jeonghee Rho is a senior research scientist at SETI Institute, and her education is BA from astronomy BA in astronomy from Yonsei University, and Master of Science in physics from Clemson University, and Ph.D. in astronomy from University of Maryland. Her expertise is on the supernovae and their remnants. And she's got a couple of major awards. One being a NASA Guru Award as member of Spitzer Space Telescope at Spitzer Science Center Caltech in 2005. And there are other awards there. So Dr. Rho, if I miss anything that you could introduce for some major things that you want to let them know, can you add some more stuff to whatever you said?
Okay. Yeah, I was at Caltech for quite some time. I did my postdoc in Saclay in France, 2 years. Then I moved to the Caltech, so at the IPAC, then Spitzer and TUMES works I did. Then I moved to NASA Ames, to Sophia Science Center. Then now, last few years, I am at SETI Institute. It's near the NASA Ames. We are very closely working with NASA Ames. And yeah, that's it. Okay. Nice to meet you. I know it's Saturday evening, thank you for attending this, although you might have many other interests. Okay, so I gave a talk at the UKC meeting. So basically, kind of, I was in mind what to suggest to Space Science Center in Korea, CASA. So I have been working on infrared data and X-ray data and work involved in mission as well. So I'm going to talk about that. Here it's, I know, I'm not sure how much people can see on the top of the page, but anyway, infrared and X-ray space missions. So left is the Cassiopeia A, was one of young, about 340 years old supernova remnant, but it has a lot of characteristics of supernova itself. So you can see many filament here, many, this is ejecta and emissions to the right, and blue is including X-ray emissions from Chandra. Okay, so let me, how do I need reduce the, so the idea is that, every 10 years in US, we made a decadal survey. So basically, scientists suggest what's the vision for 10 years. So the book published like 500 pages, but main thing is they selected the science vision is pathway to habitable world and new window of the dynamic universe, which is transient universe, unveiling the hidden driver of the galaxy growth. So that's basically early universe right after Big Bang. So they recommended the great observatory in the mission, in space mission, is first of all is a large near-infrared optical UV telescope, which is simultaneously they observe these 3 wavelengths. So that's basically toward the transient object. As you see, as you can remember, gravitational wave source was discovered. I'm just adjusting a little screen. So that's the main one of goals. We want to identify the what the gravitation wave source are, and the supernova remnant. Supernovae was observed, but sometimes open like gravitation wave, they cannot identify what the target is. So many multi-wavelengths, we call multi-messenger science, have the all wavelengths observe missions observing the same target, so we can identify what the target is at the same time. So then this is in fact this mission is already happening. They made a recommendation. They're selecting many details. But from 2025, they were thinking big missions are far infrared and X-ray mission. So this is about 3 to 5 million range. So they infrared community and X-ray community have already concept design for those missions. I will talk about at the end. Infrared is Origin and X-ray is Linux. So I'm not sure NASA itself don't have enough money for these two missions. So either they could select one, or they can bring the international partner and then make two missions successful. Okay. Okay. So sorry. Okay, that's better. Okay, so here is the optical light. The image in the left is Orion. You can see a lot of stars. If we have really some telescope, we can see some nebula, but it's relatively empty looking. But in the infrared, you can see right side, there are a lot of materials. That's basically cold material. So infrared is basically heat sensor. If you remember military, they wanted to find the enemy, then they use the infrared lights to see the enemy. So it's basically sensing the heat emission. So why do we need a space mission? Basically, you can see one basic the wavelengths go to 1 to a few hundred microns, and this near infrared is 1 to 3. Then you can see some emission. You can this is the transmission curve, but in the like JWS range to the 1 to 28 micron here, you can see really you cannot observe that much on the ground. So especially now I'm talking about this far infrared, usually 30 micron, the longer than James Webb wavelengths, then to a few hundred micron. That's we call the far infrared. So you can see completely opaque, so you cannot observe on the ground. So here is the first mission, it's IRS. 1987, this is first time they met the infrared sky. You can see nice galactic plane. Then, a lot of some bright sources. So this is first time we see the infrared sky. And here is MSX. It's 8 and 12, 15, 21 micron. MSX is basically they originally made by military, U.S. government. Purpose of the, they want to monitor everything in the enemy or whatever. So they made this all sky survey, but then, they found a lot of these astronomical objects. So they eventually published to give to astronomy community to use it. So here is then Spitzer. I worked in at Caltech. So it's a small telescope, but it did work very well. It took many 10 years from the originally they designed the bigger telescope, but then, because the mid-infrared required cooling, so they couldn't do too big. It was not very challenging to make it even 60 centimeter telescope. So here is some galaxy pictures. You can see red spots, a lot of star-forming regions. Here is gallery of the Spitzer image, Creme Nebula and planetary nebula, and some weird looking galaxy. Then there are a lot of star formation region. And this is the runaway stars. It just shows the bow shafts of the runaway stars. So here is one of Cassay's Spitzer made a lot of element. You can see different colors in different heavy elements it's making. So it made the first these three dimension images. So I think somehow maybe that's no. Okay. So then 2011 for 2 years again it required the cooling, so it's hard to make long missions. So Herschel 3.5 meters covering 50 and 600 microns. So basically next generation of infrared is similar to Herschel, but the resolution is comparable with the Hubble and JWST. So that's what they call the origin. In fact, JPL is the one center of this activity together with the Space Telescope or NASA Goddard at the Maryland. Okay, here is the Herschel image. One of the main things they found a lot of things, this interstellar medium, the medium between the stars, basically. Similar image to in the Orion. There are a lot of cold cloud between the space. So you can see, but structure are very filamentary here. A lot of star formation happen when especially crossing this filament. That you can see red is basically young stars. So it gives new concept of how universe was dynamically moving around, forming the stars. Here is the black holes, what the impact of black hole to the star formation. Basically, it seems to be, stopping the star formation, ongoing star formation. So here is the right side. It's one of supernova remnant. You can see blue, big dust shells around, which basically idea is there are a lot of dust was observed in the earlier universe. So we think it's a supernova are the good candidate because older stars, low mass stars has not been born yet in early universe. So here is another is the disk. You see the ALMA pictures, a lot of ALMA pictures, but here is the also Spitzer pictures with bigger disk in this case. So mid-infrared trace the warm dust. Even ALMA is even colder than far infrared. So here is a JWST missions, 6.5 meters. You see a lot of these nice pictures. When we compare the resolution here, Spitzer, and left is Spitzer, and right side, like 50 times more higher resolution. So JWST has a lot of, component here, especially sun shield is very big. After launch, they stretched out, so it can protect detector from the sun, so it doesn't heat it up as much. So okay, here is a few instruments. It is the this is imaging, near infrared and mid infrared, and then near infrared spectroscopy. Then this is the pointing. Basically, you can do optical sensors and gradings using the guide stars. Okay, here is the high redshift galaxy, one of the press release first image. You can see so many galaxies, a lot of, including really galaxies far away. So it's just surprising here it is. Before that, I will just explain. So JWST really found a lot of this redshift 10 to 12. Basically, redshift here is after Big Bang inflation, then there is dark age, then the first stars born and first galaxy is born. That's the area 10 to 20 to redshift 10 to 20 is basically a few hundred million years later than after the Big Bang. So you can see here is reionization happen after dark age. Then there is only short place supernovae. The dust could be important too, because later on you have low mass stars. Age is old enough. So we know relatively low mass AGB stars are dominant dust source. But then before that, we don't know, what the origin of the dust in that case. So dust really affecting the star formation. So whole history would be changed depending on what happened at the time. So here is the early universe. You can see JWS made in dark age here, then neutral gas was made, then ionized the intergalactic medium IGM. Then the way we identify galaxies that, the redshift, basically we can characterize some lines. Usually its wavelength is optical 5,007 Armstrong, but then in near infrared wavelengths, if we shift, we can measure the distance to the supernovae. So here is the JW, maybe I'm getting a little long. Okay, so I was explaining the introduction too long. So here is the one of JWST was. So one of the new things is this circumstellar medium was this green monster. We call the green monster. Basically, that's like Eta Carina, the pre-existing mass loss material. Then supernova was bouncing at this material. So it's reverse shock and shock material. Then not only that, it has CO molecules and the ejectors. Here is you can see details, you can see difference in molecules. The basic idea here, this is using the infrared spectroscopy. This is a CO fundamental band. You can see a lot of wiggle looking. That's all different transition in molecules are very complicated. So you have so many levels. So basically in here, you see that supernovae making heavy element. Then it cools down, so it makes molecule, eventually molecule contribute to cooling, gas cools enough to form the dust. Okay, so this is the Origin telescope. NASA funded conceptual designs at the moment, but it's just a detector is being laid out. It has not been made yet. So basic a compelling question they want to answer is, how did we get here? Basically, are we alone? That's the one of basically SETI, searching for intelligent life outside the Earth. That's one of the goals. Then how did the Milky Way, other galaxy forms, which relate to the kind of cosmology? How do life-bearing planets? One of hot topic in astronomy we do is exoplanet. Exoplanet only found was discovered less than 10 years ago. But now like 3,000 exoplanet. Exoplanet means there are so many planets like the Earth, but it's moving around other stars. Now it's discovered like 3,000 exoplanets. Planets like the Earth are discovered. So we want to follow, searching for signature of life as well as the composition in there. And so that's one of the hot topic in 2020, supernovae transient science. Then also exoplanets, looking for a signature of life. So this is the new mission called Origin. So here is, you can see really JWS James Webb only go 28. Now it goes to up to 1,000, 28 to 1,000 with the same resolution as Hubble and JWST. That's the mission they want to do, have imaging and spectroscopy and a few different instruments. I don't think they have polarization instrument. Yeah, I did notice. Okay, so X-ray missions, I'm going to very short. So Rosette, all the survey German made, and Chandra, XMM is a European mission. He told me was very high resolution, but as you might recall, had problems. So it's broke. It was broken in the space, basically, into the a few pieces after 4 months of the lifetime. So I think Exism now it's working. They made another mission, almost exactly the same. So X-rays basically, basically 10 to the 7 million degree gas it's tracing, as well as non-thermal gas. So here is a lot of different objects, and X-rays also trace the young stars and impact of the black holes. They think when stars are engulfed by the black holes, they could make more X-rays. So here is Linux, basically more high resolution imaging and spectroscopy. They also wanted to make similar to Hubble or JWS resolution. That means like 0.01 or 0.1 arcsecond. Okay, that's it. Thank you. Hello?
Oh, sorry, I was on mute. Sorry. Thank
okay.
you, Dr. Rho.
Okay.
For your outstanding presentation. Very interesting, nice pictures. So we can take a few minutes for a maybe short question answer, and then can move on to the next presentation. Anybody has any question, comments? You can unmute and then speak or raise your hand.
So I was just recommending, this is a really big mission. So we could, Korea could take some partnership so they can start to develop some instrument, and as well as the mission is the telescope itself with the mission functions. Yeah.
So I got one question, Dr. Rho. Well, what would be the biggest, next challenges or breakthrough that you are trying to accomplish from now?
Science or in terms of the telescope missions?
So your field of expertise, what would be considered as the next biggest, milestone or breakthrough that you are trying to accomplish?
Oh, we want to see, basically in astronomy, how the universe was made right after Big Bang. That's the, very common. Though other things I mentioned, it's, extraterrestrial life, the exoplanets. So is there some signature of biosignature outside of the Earth? That's yeah, main thing to also what there are so many new physics, for example, gravitation wave source. They previously supernova only make the iron heaviest element, but then they made the gold and the atomic number is like 70 or 80 kind of the heavy element they found in gravitation wave sources. This merging neutron stars. So a lot of new physics.
Okay.
Basically, we are looking forward to find.
Okay. All right. Thank you for sharing that. I think due to the time constraint, I think we should move on to the next speaker. Thank you again. Engineering at Purdue University. His research focuses on understanding the effects of gravity on multi-phase thermal hydraulic characteristics, with a particular emphasis on cryogenic flow boiling physics. His primary goal is to leverage multi-phase fluid thermal science to innovate in space thermal management systems. Prior to his doctoral studies, he worked as a research engineer at ADD, Agency for Defense Development in National Lab in South Korea, where he focused on developing advanced thermodynamic systems for naval defense applications. He has been honored with several professional awards and academic fellowship, including Gold Prize winner of the fourth HVAC competition from SAREK in 2016, as well as the Frederick and Andrews Fellowship in 2020, and Biesland Dissertation Fellowship in 2024 at Purdue University. So he's been receiving a lot of recognition. So it's our pleasure to have Sunjae Kim as our next speaker. So it's all yours. Go ahead.
Thank you, Doctor, and thank you very much for your great introduction. And one caveat that I want to ask you is I asked for about 30-minute presentation. Would that be okay, or is it too long?
I think it's okay. I think
Okay.
people have more interest can stay longer. So I think it's good.
Okay, yeah, please feel free to stop me if it's going too long. So let me start.
Yes, go ahead.
Thank you very much. So hello, everyone. Nice to meet you all. I'm very humbled to be here and honored to be here at this webinar with Costa today. So as Dr. introduced to me, my name is Sunjae Kim, and today I'm standing here in front of you to introduce my interesting research on cryogenic flow boiling physics under terrestrial, partial, and microgravity conditions. So let me start. So let's start by watching a short video clip that well summarizes what I have done for past several years. My research aims to understand cryogenic flow boiling phenomena under reduced gravity conditions. This technology is actually one of the very critical technology area in developing NASA's in-space application. To understand this cryogenic heat transfer phenomena under microgravity conditions, I conducted a series of microgravity flight testings on board parabolic aircraft, as you can see within the video. So from today's talk, I will introduce to you what I have discovered from this project and also how I developed design tools that are tailored for cryogenic in-space applications. So what exactly are cryogens? Some of you might already have heard of it and be familiar with the term, while for others, it could be a new concept. Cryogen is a type of fluid that exists as a form of liquid and at a very low temperature. And technically speaking, it's a fluid class that has extremely low saturation temperature. Common examples of cryogens include liquid nitrogen, liquid oxygen, liquid helium, liquid methane, just to name a few of them. So then where do we use cryogens in space, or where do we want to use cryogens in space? To give you a concrete example, as Dr. Rho also mentioned a lot, let me show you a stunning image of Carina Nebula, which is about 8,500 light years away from our planet Earth, really deep inside the universe. This image is actually one of the very first image captured by James Webb Telescope. If you look at the very center of the telescope, there's an instrument called MIRI, as Dr. Rho has mentioned in her presentation as well, This MIRI is technically working as an eye for the Space Telescope, and for this MIRI to capture a crystal clear image without any thermal noise, MIRI has to be extremely cold, and that's where cryogene comes in. MIRI utilizes liquid helium to cool itself down to minus 267 degrees Celsius, very low temperature. Another great example of cryogenic in-space application is a nuclear thermal propulsion system. Nuclear thermal propulsion is an innovative rocket propulsion system that utilizes liquid hydrogen as its rocket propellants. By pairing this liquid hydrogen with a nuclear reactor core, this system can provide us a specific impulse of 900 seconds in vacuum, which is nearly doubling the rocket efficiency of conventional rocket systems that utilizes chemical propellants. So by looking at these fabulous examples, now we clearly understand that the cryogen holds immense potential for a variety of space applications. However, despite of the long years of research and science in cryogenic physics, we still do not fully understand the physics behind cryogenic two-phase flow and heat transfer. So why is it? Why is that so challenging and difficult to do that? To give you a short answer, it's because of the unique thermal properties of cryogens. For example, under ambient pressure of 1 atm, we all know that water boils at 100 degrees Celsius. However, when it comes to liquid nitrogen, it boils at minus 196 degrees Celsius. What you're seeing here is about 300 degrees Celsius temperature difference between water and liquid nitrogen for them to boil. So yes, cryogens have really low saturation temperature. Similarly, cryogens also have a low liquid viscosity, which causes them to have a faster transition from laminar to turbulent. Also more relevant to boiling physics, cryogens also have a very low latent heat of vaporization, which is HFG, requiring lesser energy for them to vaporize, meaning it's easy to boil. And also, cryogens have a really low surface tension, causing them to have a really small and tiny size of vapor bubble sizes. So due to these unique thermal properties, entire fluid physics behind cryogen is uniquely different from those of normal room temperature fluids, such as water or common refrigerant. So in other words, the conventional design tools that we have in our hand, which are all developed based on water or common refrigerants, may not predict the cryogenic physics correctly. So then what would happen if we just use non-cryo design tools to develop those cryogenic applications? Well, the results could be quite shocking. According to the recent study by NASA, when they used water-based correlation to develop their in-space cryogenic application, as you can see, the maximum error deviation could rise up to 18,000% for quenching data, and even for steady-state heating data, still the maximum error deviation rise up to 1,000%. So what are these massive numbers and errors are telling us? When you're developing a space system, and when you're encountering such kind of massive errors in your design, most of the cases you need to compensate those errors by adding more additional safety margins. Those high safety factors drives up the cost and significantly decreases the economic feasibility of your space system. And more often, these high safety factors significantly increases both mass and volume of your space system. And those are the main reasons why we have to develop new design tools that are tailored for cryogenic applications. Okay, well then, in order to develop such kind of cryogenic specific design tools, the very first thing that you need to have in your hand is a solid cryogenic database. However, when we look back to the literatures and previous databases, it's quite surprising to see how little there are available for a cryogenic flow boiling system. And what's even more concerning is, as you can see within the table, is the complete absence of cryogenic heat transfer data, especially under microgravity condition. I repeat this once again because this is so important. Complete absence of cryogenic heat transfer data, especially under microgravity conditions. So in order to address this significant data gap and ultimately to develop cryogenic specific design tools, it was imperative for me to conduct my own cryogenic flow boiling experiment, particularly under reduced and partial gravity conditions. Well, in order to conduct microgravity experiment, the first question that I need to ask myself is, how are we going to do it? How are we going to create microgravity environment? Well, the easiest solution that I could tell you is a drop tower, the most simplest and the most classical way of creating microgravity. Bring something onto a high tower, drop it, you will acquire a brief moment of microgravity. However, as you can see on the slide, the moment of microgravity from drop tower is only 5 seconds, which is too short for any boiling system to reach steady state. So I need something longer. Maybe sounding rocket. Sounding rocket is a great microgravity platform that provides more than 5 minutes of microgravity period. However, there's one big caveat. As you can see on the slide, the size of the payload has to be extremely confined and limited so that it can fit inside the rocket. However, most of the components that I'm trying to use for my cryogenic flow boiling experiment are pretty large and voluminous, so they're pretty hard to be fit inside this small rocket. I need something larger. Yet there is another great microgravity platform called parabolic flight aircraft. Parabolic flight aircraft climbs up and down between 24,000 feet and 32,000 feet of airspace. And by doing that parabolic maneuver, this platform can provide us about 15 to 18 seconds of microgravity. And by repeating those parabolic maneuver, this platform can also provide us a multiple number of parabolas, up to 30 parabolas from one flight campaign. On top of that, there's one additional big benefit, which is the size of the payload. Since this aircraft is a cargo aircraft, Boeing 727, this aircraft can accommodate up to a pretty sizable payload like the one that I'm trying to develop here. So by comparing pros and cons out of these three options, I decided to conduct my own cryogenic flow boiling experiment on board the parabolic aircraft. So from now on, I will walk you through how I achieved all these project goals that I've listed here, starting with introducing to you how I developed and designed my own cryogenic flow boiling experimental facility. Well, the very first thing that I did to design this new experimental facility is to lay out the PNID diagram. PNID stands for Piping and Instrumentation Diagram, which allows me to identify the critical components, instrumentations, and sensors that are required to measure all the parameters that I need for further heat transfer analysis. Based on that finalized PNID, then I proceeded to design, as you can see on the right side, the 3D CAD model, which allows me to organically position all the components and plumbings within the allocated volume and space inside the aircraft. What you're seeing here are two critical components from my experiments. Number one, to your left side is a main test section chamber where the actual flow boiling takes place. Downstream of the test section, there is a visualization section, as you can see on the right side of the image, which allows me to see through the flow boiling. As you can see, there's a glass window and glass tube that I used, which allows me to record and capture those flow patterns using high-speed camera. So based on the 3D CAD model that I developed, using that as a guideline, I then started to build and construct this facility from the scratch. And these pictures were taken during the actual construction phases. And at the bottom, you can also see my colleague Nishan and I actually fabricating the main test section, installing the thermocouple on and around the tube. So here now on, I'm introducing to you the finalized version of my constructed flight rig, which is located in the lab back in Purdue. So before taking this flight rig into an actual flight testings, the important task is to do a ground operation. By conducting a series of ground testings, I was able to verify and validate the system stability and operability for the exact same cases that I'm planning to run on the actual flight cases. So by doing that, now I'm ready to go on a parabolic flight. So now let's talk about the parabolic flight campaigns. My first flight campaign happened in June 2022 in Santa Maria, California, which is about 3 hours north from Los Angeles. These pictures were taken from the day before the actual flight testing, is what we call TRR, Test Readiness Review. On these days, we move our facility from the hangar to the aircraft, and you can also see that the facility being installed inside the aircraft right down the cargo door. And these pictures were actually taken on the day of flight testing, our very first day, and that's the main reason why all our faces are so stiff and nervous, because we didn't even know whether the experiments are going to be successful or not. But yeah, that was our first campaign. And our second campaign happened in the same year, November 2022. This time we went to Florida, Fort Lauderdale, Florida, which is about an hour away from Miami. And this time, as you can see from bear with me. Yep. As you can see with these pictures, now you can see all of our team members are smiling, bouncing on and off, flying around. Clearly, we're more comfortable, relaxed, and more importantly, we're confident running this experiment on board the aircraft. And this is something that I need to highlight. This year, early this year, March 2024, by successfully securing another grant from NASA called NASA Reflight Extension Grant, I was able to go on our third flight campaign. So across the year and a half from 2022 to 2024, I successfully conducted 3 flight campaigns, which yielded me a total 270 parabolas, through which I successfully acquired the world's first microgravity cryogenic heat transfer database. So now I have a database in my hand.
So basically, you are testing cryogenic system.
Yes, I'm testing. Yeah, that is correct.
Okay.
Thank you for the question,
So
Dr. Rho.
what is the temp? Oh, this is the temperature you measured.
Yes, you're seeing the transient data for my temperature. So temperature range goes from minus 200 degrees Celsius up to plus 200 Celsius. So let me continue.
Okay.
So what you're seeing here is the transient data for one set of full boiling curve that was collected during one of the parabolic flight experiment. For this specific case, I utilized 8 different continuous parabola through which I controlled my heater power from 0 heater power, as you can see from the red line. And with the small increments, I increased my heater power 8 times to reach Qmax. As I increase my heater power, you can see my wall temperatures are also increasing accordingly, since that's obvious because I'm increasing my heater power. And I'm using those measured wall temperatures to later then compute an important parameter called heat transfer coefficient, which represents the efficiency of your system's heat diffusion processes. What you can also see, let me turn on my laser point. I forgot to do that. So what you can also see from this figure is at the last heater power Qmax, you can see one of my thermocouples spikes up uncontrollably. This temperature excursion actually indicates that my last heater power Qmax has reached something called critical heat flux. Critical heat flux is actually another important parameter for any two-phase thermal systems that represents the maximum allowable heat flux amount that a system can handle before it goes into a failure mode or burnout. So please keep these 2 parameters in mind, since we're going to use those for upcoming discussion for heat transfer. So before we dive deeper into heat transfer discussions, first let's see how gravity affects on cryogenic two-phase flow patterns. What you're seeing here is the image captured during parabolic flight campaign under microgravity conditions. As I increase my heater power from 2 to 11, you can see that the flow pattern transitions from bubbly flow to large bubbly flow to slug flow and lastly into annular flow. What's particularly fascinating about this image is the way how these vapor bubbles are distributed. Under microgravity, due to the absence of buoyancy force, these vapor structures are nicely dispersed along and across the tube, and also as they increase in their size, these vapor chunks, which I call slug, are nicely aligned along the center line, showing a symmetrical flow pattern. Symmetrical flow pattern is the characteristics of microgravity flow patterns. So now let's see how these flow patterns change as I increase my gravity level. In microgravity, as we have expected, vapor structures are nicely distributed, nicely aligned along the center line, showing us symmetrical flow patterns. However, as I increase my gravity up to lunar gravity, which is 1/6 of Earth gravity, now these vapor structures are slowly rising towards the top wall. As I increase more up to Martian gravity now, which is 3/8 of Earth gravity, suddenly your vapor structures are completely flushed upwards, almost touching the top portion of the tube. Under Martian gravity, due to the strong buoyancy force effect, lighter vapor structures are projected towards the top wall, while heavier and denser liquid tends to flow underneath those vapor structures, causing a strong flow stratification. So these flow stratification is the characteristics of higher gravity flow patterns. Well, now at this point, you might be wondering then, what would happen under Earth gravity? Let's take a look at that. So to see the effective flow orientation on flow patterns, I also designed this rotating platform, which I integrated with the existing flight platforms and conducted the same flow boiling experiment in 5 different orientations. Today, I brought 2 of those, vertical upflow and horizontal flow. So let's compare them. For vertical upflow, your buoyancy force vector and flow orientations are parallel to each other. So as you can see from the videos, the vapor structures are nicely distributed, nicely aligned to center line, showing us symmetrical flow pattern, which was very similar to what we have seen under microgravity. However, when it comes to horizontal flow, even from the first sight, it looks completely different. In horizontal flow, your buoyancy force vector is now perpendicular to your flow orientation. So the significant amount of lift force is exerted on these vapor structures, causing a clear sign of flow stratification. Again, horizontal flow is very similar to Martian gravity flow. So by observing all these series of flow visualization, we now clearly understand that the gravity has a significant impact on cryogenic two-phase flow patterns. Let's take that understanding a step further to see whether the effect of gravity extends further even to effect on cryogenic heat transfer performances. Let's look at that. Well, since we're scientists and engineers, let's quantify and compare using a parameter called heat transfer coefficients. Well, so to answer the grand question whether gravity will affect on heat transfer coefficients or not, let me first summarize what we have learned from flow visualization analysis. So under microgravity and lunar gravity, due to the relatively low or no gravitational acceleration, these produced vapor structures are fairly well dispersed, showing a minimal amount of flow stratification. So as a result, as you can see from the schematics, your tube walls are fully wetted, meaning that they are in full contact with the liquid, facilitating the efficient heat transfer efficiency. However, as I increase my gravity level up to Martian and Earth gravity, due to the strong buoyancy effect, your vapor structures are completely flushed upward, almost touching the top portion of the tube. And as a result, your tube wall is not anymore fully wetted, rather they are partially blocked by those vapor structures. So, which makes us to conjecture, maybe those blockage will drop the heat transfer coefficients. Let's see how this visual observation translates into quantified heat transfer coefficients. So in microgravity and lunar gravity, due to the effective liquid replenishment to the heated wall, the high magnitude of heat transfer coefficient can be maintained. However, as I increase my gravity level up to Martian gravity and Earth gravity, you can see that the heat transfer coefficient significantly drops below those of microgravity and lunar gravity, showing a clear sign of relation between gravity and heat transfer coefficient. As I increase my gravity, you can see that the heat transfer coefficient drops, demonstrating an inversely proportional relationship between the two parameters. From further analysis, I was able to find the mathematical representation of these data trends using hyperbolic tangent function, later that I employed to develop a new correlation. However, the gist and key takeaway is the inversely proportional relationship between these two parameters, and with the fact that the gravity does affect on cryogenic heat transfer performances. Okay, so now let's take a look at another parameter, another important parameter called critical heat flux. Let me remind you what the critical heat flux is. Critical heat flux is another important parameter for two-phase thermal system that represents the maximum allowable heat flux for a system can handle before it going on a burnout situation. So if your heater power is above critical heat flux, your system will burn out. However, if your heater is below critical heat flux limit, then your system is going to be safe and sound. So let's take a look at the data. These data are the actually measured CHF limit under Earth gravity for two different orientation for wide range of mass velocity. What this data indicates is that regardless of your mass velocity, regardless of your flow orientation, under Earth gravity, you can safely operate your heater up to a level of 100 kilowatts per meter square second. So as long as your heater power is below 100, your system is going to be safe. However, as soon as you exceed 100, your system will be burned out, going into a failure mode. So now let's see how microgravity changes this microgravity CHF patterns. Boom. So the results for microgravity is quite surprising and thought-provoking. Let's take a look. In microgravity, as you lower down your mass velocity, and as soon as you surpass a certain critical mass velocity, your microgravity CHF suddenly plunges down to a level of 50 or even less than 50, which means in microgravity, you can only power your heater up to a level of 50, which is only a half of what was used to be under Earth gravity. This significant groundbreaking discovery actually tells us three important safety guidelines for future space missions. Number one, when you're developing a cryogenic two-phase systems that are aimed to be operated under microgravity conditions, you need to do as much as possible to avoid such kind of low mass velocity operating conditions. However, number two, if it's really necessary and if it's required to operate at such low mass velocity, maybe if your systems is small, if your pump power is not that much, it might have to be operated at such low mass velocity. If that's the case, you must take into consideration of such significantly reducing CHF limit in order to avoid any burnout situations, which will be catastrophic for any cryogenic space systems. Number 3, fortunately, there's a very simple way to overcome this difficulty. By simply increasing your mass velocity over the critical mass velocity, now you can recover back your CHF limit up to a level of 100, putting your system in a region what I call gravity independent region, rather than putting your system in a gravity dependent region. So clearly, gravity does also affect on cryogenic critical heat flux limit as well. So from these exercises that we have walked through together, we clearly now understand that the gravity does affect on not only cryogenic flow patterns, but also for cryogenic heat transfer performances as well. And we've looked at that in 2 different perspectives. Number 1, heat transfer coefficient. Number 2, critical heat flux. Okay, so based on that understanding, now I want to talk a little bit more about my new design tools that I developed that are tailored for cryogenic flow boiling systems. Due to the time constraints, I'll mainly focus on the key results of the correlation, starting with the saturated heat transfer coefficients. So here I'm introducing to you the newly developed saturated heat transfer correlations. Let's see how this correlation works. So this correlation provides surprisingly high accuracy, not only for 1G terrestrial Earth gravity, but also for microgravity conditions, covering a wide range of gravity spectrums, which addresses the limitation of the previous correlations. And on top of that, a key aspect of my new design correlation is the universality. The same set of correlation has to be working for not only for liquid nitrogen, but also for other type of cryogens, including helium and argon. As you can see from the left side figure, the right side figure, you can clearly see that the correlation is universally applicable. Also, by taking the similar processes, I also developed a subcooled heat transfer coefficient. Taking a similar step, this correlation also works for a wide range of gravity, all the way up from Earth gravity, all the way down to microgravity. And again, this same set of correlation works not only for liquid nitrogen, but also for methane and hydrogen. And one important thing is these methane and hydrogen are the rocket propellants for SpaceX and NASA science rockets as well. So, okay, I have these advanced correlations established in my hand. My next question is, how am I going to use it? How am I going to adapt all these correlations into actual real-life applications? So to answer that question to myself, this year particularly, I worked really closely with my NASA collaborators, Dr. Jason Hartley from NASA Glenn and Dr. Andre Leclerc from NASA Marshall. By working closely with them this year, I was able to directly implement my own correlations into actual NASA's 1D design code. And as you can see, this model has a very exciting potential to be applied for in-space refueling system by designing and optimizing the transfer line. The transfer line is the connecting line between service tank and the customer tank. What we don't know about this transfer line, which has to be designed, is the length, the maximum allowable length of the transfer line while avoiding the CHF happening in the system. And this particular model that I developed with NASA can actually tell the maximum allowable length for those transfer lines. So that was the very concrete examples, how those fundamental science correlations can be adapted for actual real-life applications. On top of that, I also developed the computational fluid dynamics, CFD models, to tackle in-space cryogenic applications. Again, due to the time constraint, I will skip most of the modeling part, but I'll show the results right away. So here, I brought 6 different cases. Let's take a little closer look how it looks like. So by using my novel CFD models, this model can actually track active bubble formation, nucleations, and also their growth, and also their detachment from the heated wall. And these detached bubbles, while they flow through the tube, they merge each other, as you can see here. And if they do not merge, we can also track how these bubbles travel away from the heated wall all the way up to the core of the tube. So by looking at this, I can tell you that my novel CFD model can give you accurate predictions for 2D and 3D thermohydraulic information for cryogenic fluid boiling systems. Well, these images were all calculated under Earth gravity. So I need to validate whether my model works also for microgravity conditions. So I used the same set of model and adapted for another set of experiment, which is called FBCE, the flow boiling and condensation experiment, which has been conducted on board the International Space Station. So by running this simulation, I was also able to validate my model works not only for Earth gravity, but also for microgravity conditions as well. Okay, so I gave you a lot of information. Now we're at the final stage for conclusions.
Wow.
So
Go ahead.
thank you. Let me conclude my presentation here. So through my PhD project here, by identifying the critical gap of a cryogenic flow boiling physics, particularly under reduced and partial gravity conditions, to address this significant gap, I designed and developed this parabolic flight experiment. And by running those microgravity flight testings, I was able to acquire the ever first in human history. It was a world first microgravity cryogenic heat transfer database, which allowed me to understand the gravity effect on heat transfer coefficients and critical heat flux. And based on that understanding, I was also able to develop a universal heat transfer correlations, which is now directly implemented into NASA's 1D nodal code. And on top of that, I also designed and developed a novel multi-phase CFD models that I validated for providing an effective 2D and 3D thermohydraulic informations. So in a nutshell, by doing all these things, I was able to deliver a total design package for NASA's in-space cryogenic transfer line systems. So I guess that's what I have prepared today. Thank you for your listening and attention. Thank you.
Wow.
Thank you.
What a great presentation. I think it was probably one of the best presentations I've ever seen, I guess. Are you how close are you to finishing your PhD? Are you almost done?
Yes, I'm almost done. I'm actively looking for positions in an academic career. Actually, I'm applying for many universities now. Yeah.
Oh, yeah. I'm sure you can be a great teacher. Yeah.
Thank you very much, Dr.
Very well done. Any questions for Sunjae Kim, the future professor?
Thank you.
질문인데,
Yes, please. Go ahead.
yeah, so just a question. Based on your data, I saw you were maintaining somewhere, the pressure you're maintaining somewhere like 70 or 80 PSI for the test.
Okay.
Why do you choose that pressure? I mean, is somewhat practical? There's any practicality for that pressure, or you know?
So both practical reason and also engineering reason as well. Practical reason, I'm saying actually this project was aimed to develop a in-space fuel depot. And I can't say too much in detail of it, but the operating pressure range were somewhere there in my experimental facility, where, as you said, it was not only 70, 80 PSI, that was the data that I brought, but it was wide range of pressure ranges. But yeah, the main application that I was aiming for were operated at such pressure. In engineering perspective, the aircraft, the flight provider, where I'm putting the system on, they were not actually allowing me to go over the 150 PSI. So if they allowed, I would have wanted to go much more higher, but yeah, that was more of a practical and engineering reason why I had to stick to those ranges.
Okay, yeah, because a very well-known problem you addressed, but in practical, application, to avoid those, cavitation issue, we usually apply high pressure, to remove those bubbles and stuff. So
yeah, true. So
why was choose 80 PSI, which seems kind of low to me. Usually go above like 1,000 PSI or sometimes maybe somewhere around. But I was just curious about that.
Thank you for your question. Hope I gave you an answer.
Yeah, I think the more detailed technical discussion can be followed. I think I see a hands from Professor Eunjung Choi.
Yes. Actually, it's a really good presentation.
Thank
Thank you
you.
for your, the great work. And I have a quick question. What was the actual governing equation for the CFD model?
So you mean the governing equation for my interface tracking model? That was VOF model, but I enhanced it to be CLS VOF, couple level set VOF model, coupled with additional momentum sources directly embedded into momentum equation.
So you mean you're using the Rance equation or
Rance.
because
Yeah,
the
it was
BOF
Rance.
is a volume of friction fluid model that is only for the multi-phase. So your fluid governing equation, you're using the Vance model base, right?
Correct.
Okay. Okay, good.
Thank you. Thank you for your question.
Okay. Anyone else has a question? I think we're kind of going a little bit over time, but I think, very excited about this outstanding presentation here. So anyone has any question?
Okay, I'll ask a basic question. So I
Yes,
hear
please.
all this physics, but I didn't get the bottom, main point. So when gravity is low, is our current helium cooling cryogenic system does work or does not work? And you're suggesting many solutions. I don't know what's your bottom, main point. If we go to the moon and we want to make cryogenic something, then what do we have to do?
Yes, thank you for the great question, Dr. Rho. I think you spot on to the question. So I hope you're seeing the data that I have shown you before. So to answer your question, the main point from my discovery, as I've said, the critical heat flux, which is the safety guideline. Once again, to repeat the question, if your heater power, if your heat load coming out from, let's say, a James Webb Space Telescope, if the heat load coming out from James Webb Space Telescope exceeds the microgravity CHF limit, your system will be burned out. That's the main point. So as long as your heat load can be controlled below these CHF limit, then your system can be safely operated wherever you are. But the main gist is that your heat load has to be designed in a way that has to be controlled below those CHF limit. But when it comes to liquid helium, the story quite changes because their critical pressure is really low, as you know. So their temperature easily exceeds the critical pressure and critical temperature. So these results for critical heat flux could be a little bit different from liquid nitrogen. These results are all from liquid nitrogen. So the universality, the correlation is still there, but we still do need to study further for liquid helium specifically.
So what is second question? What is the best way to cool any instrument?
So as the James Webb Space Telescope is doing, the pulse tube type liquid helium for now is the best way. But if there could be, in my own perspective, if we could use the two-phase cryogenic system where, let's say, a microchannel heat exchanger with a liquid helium on it, on top of the cryocooler, that'll be the best. But obviously, there are more technical barriers that we need to overleap to get that stage. But for now, pulse tube liquid helium is the best way.
Right, but all your research, what's your new method, right? It's impressive.
I think that's
changing, but
yeah. So I think that's $1 million question. So I guess we can discuss further in our following email. I'll make an email contact to you. I'm very interested in the question. Thank you.
Yeah, I think